Hello everyone. If you followed my channel for a while, you know that I'm a big proponent of IPv6. However, thanks to the IT cavemen, who can't be bothered to adopt a quarter-century old technology at this point, roughly 20% of the traffic that leaves my network is still legacy IPv4. And that's a problem for me because it means I need to provision both IPv6 and IPv4 all across my network just so my laptops and my phones can get to those 20% of internet destinations. But of course, there is a better way. Just like the legacy IPv4 people think we should just add more NAT, we just NAT on NAT on NAT our way until we've solved all the IP exhaustion problems, we can do the same in IPv6 with a technique called NAT6.4. Since the IPv4 address space is so minusculely small, we can fit millions of copies of the entire IPv4 internet in one IPv6 subnet. And so with NAT6.4 we do just that. We take one of our subnets, we allocate it to be the whole world in IPv4, and then our IPv6 clients can get to the whole internet, the IPv6 internet as normal, and the IPv4 internet via this special whole IPv4 world prefix. And that's great, but some software somewhere has to actually translate these packets from IPv6 to IPv4 for this to work. And this uses one of two algorithms, either NAT6.4 stateful or stateless, IP and ICMP translation. So today, I'm taking a look at the open source software that implements this IP and ICMP translation for NAT6.4 and NAT4.6. And I'm even adopting one of these as my new open source project. So if you like IP and ICMP translation, come along on this adventure. So broadly speaking, NAT6.4, CLATs, 464 XLAT, they all belong to a family of translators called IP and ICMP translators that take real IPv6 packets and turn them into real IPv4 packets and vice versa. We're not doing any encapsulation here, this is all translation. We take our source and destination IPv6 address, figure out what the equivalent IPv4 address would be, which can be very hard sometimes for IPv6. We take all the other fields from the header, the hop limit, the next header, etc., translate those guys over, and we have a real whole IPv4 packet we can send around the legacy IPv4 internet. And when they send us a response, we can then take that real IPv4 packet, translate it back into IPv6, and send it to our IPv6 only clients. Now at first glance, it might seem like those two things are the only thing that an IP and ICMP translator does. Translate v6 data packets into v4 data packets, and translate v4 data packets into v6 data packets. But there are actually about 7 things that a standards compliant translator has to do. So the first two I already mentioned, v6 data into v4 data, and the opposite, v4 data into v6 data. The next two are a bit of a logical extension on that. What happens if we send a v6 packet to the translator that can't be translated? Maybe the address is encoded incorrectly, or it doesn't have any way to map the source address. In that case, we have to send an error packet back. IP defines a protocol for that called ICMP, the Internet Control Message Protocol. There's a version of that for v4 and for v6. So if we get an invalid v6 packet, we have to generate an ICMP v6 reply and send it back. And same for the v4 side. If we get an invalid v4 packet, we have to generate an ICMP v4 error and send it back. So that's mode 3 and mode 4. Now what happens if we get sent an error packet? So we could, for example, try to access a server over IPv4. We start with a packet size that gets translated into, say, 1500 bytes. We send it across the v4 internet, but it's going to someone in Germany that still loves PPPoE, so they can only handle 1492 bytes. They kick us back a reply that says packet too big. Now we have an IPv4 packet, which contains an ICMP v4 error, which contains our original translated IPv4 packet, which contains probably some data. So now we have to translate the IPv4 header into IPv6, and the ICMP v4 error into an ICMP v6 error, and the included embedded IPv4 packet into the embedded IPv6 packet, all at once. Otherwise we break things like end-to-end error discovery and path MTU. And those are things we really don't want to break. So that's where we get modes 5 and mode 6. IPv6 error translation and IPv4 error translation, including the embedded packets. And mode 7 is special if you're using explicit address mapping. So if we send an address to a v4 destination, but that v4 destination is also address mapped back to v6, the packet would hairpin. It would go v6 to v4 and then turn right around and go v4 to v6 again. So we have special case handling for hairpin packets. That's mode 7. So aside from mode 7, every IP and ICMP translator, per the standard, must implement the first 6 modes. So v6 to v4, data, generation of errors, and translation of error packets. And a lot of translators don't do that. So let's take a look at what the open source options we have that I've found that do IP and ICMP translation. So here I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 different projects which all implement some form of NAT64 translation in open source. Now I say subset here because the full superset would handle quite a few algorithms. So I've mentioned NAT64, and that's used by the network to provide access to IPv4 only resources to v6 clients. There's also a more limited subset called SITDC or EAM. This is where we're trying to get just specific v6 clients to v4 internet, and it's really commonly used in data centers to map our public v4 addresses onto internal v6 server addresses. We also have an even more limited subset of that called the CLAT. That's where we have a computer that has exactly one translation from its local IPv4 to the NAT64 translator. This is really commonly used on mobile networks, so we have implementations for Android, iOS, etc. that are part of the base operating system, and open source ones. And the fourth set is a function called MapT. So in ISP space, ISPs can use a lot of these technologies to transition their networks. They don't have to carry v4 traffic. One of those ways with 464XLAT, where they use NAT64 into CLAT. But another way is a technique called address and port mapping, and in v6 it's called MapT. So with MapT, that's a kind of again a subset of the CLAT, except it's working on specific port translations as well. So all of these pieces of software implement one of those, but one or more of those, I guess. But broadly, all of those do IP and ICMP translation from v4 to v6. So the first one I got here is IP46NAT. It says it is a Linux kernel module for doing v4 to v6 translation. Great. It's a bit on the old side. Everything here is 13 or 14 years old except the README. And in the README, it basically says the project is concluded, and if you'd like to resume development, you can pay him, I guess. So if we look at his module here, he wrote this a number of years ago. In theory, it does this in Linux kernel and whatever old Linux version this was at 2011. Now one problem with this one is this one doesn't handle ICMP at all. So we follow the code path that does v4 to v6. So we create a new skbuff, we initialize the skbuff, we translate the transport header, so this is TCP, UDP, ICMP. We translate the addresses, and that's kind of just it. So what if we had an ICMP error here? So I guess this 13, 14-year-old kernel module does option 1 and option 2. We can translate data packets. But if we get an error, we just drop the packet on the floor and don't care about it. So we break PathMT discovery, we break a bunch of discoverability features of ICMP in dealing with errors. But also, if we get an ICMP error, then we also drop that one on the floor too, or we send it as a mistranslated packet, which greatly confuses the operating system. And again, we break PathMT discovery and all kinds of things like that. So this is sort of a bare bone implementation. And that's why I said that the first 2 cases are really easy, but getting a proper translator requires a whole lot more than just processing data packets, as this shows. Next one I got, it's also 12 years old. It is by CERNET. They are a Chinese network research organization. They actually wrote a lot of these RFCs that deal with this translation, and they wrote an example open source implementation of MapE and MapT. So these guys here at CERNET, they actually did a little bit of work for ICMP. So if it's ICMP and it's an echo or a ping, they translate pings. And then down here, if it's an echo reply, so that's a ping reply, they translate those two. But if it's something else, they just say unsupported ICMP type. Ooh, no, they dropped the packet. Oops. So these guys at least translate ICMP so you can ping, but not any error messages. So you still won't get packet too big, PathMTU discovery is still broken, you still won't get source and destination address errors, things like that. But at least you can ping now, and that's a bonus, right? And the third on my list actually pops up in 2 different places. So here is the author's repo here, where it was updated last month, and it's specifically for OpenWRT, and this is a kernel module as well. But it's also here in Nest open source, so I guess Nest used some version of it, and they've published their own version that needs at least Linux kernel 5.4. So this is the kernel module that's used by OpenWRT, and it's also supported by CLAT-D. This module is actually doing much better. So here we are in the v6 path. We check for TCP, we check for UDP, we check for ICMP, and then we fix up ICMP. And so here we look at the informational ones, echo request, echo reply, deal with those. And the other ones, we have all these other fix-up functions here for destination unreachable, packet too big, time exceeded, and parameter problem, which is really all the big errors. So if I dive into one of those, there's a bunch of different codes you might have to transmit, and it's translating all those codes. Same with packet too big, we have to translate the MTU. It does all that. Excellent. So this module looks pretty complete to me. However, this is again a stateless module, and it's really only designed to work for one host. It's a CLAT. So this is used in OpenWRT to implement MAP-T and 464XLAT and a few other implementations. So this can only deal with one address translation at a time, but it's perfectly fine in the case of a single client accessing their IPv6 only network. And it's great for that. But this project can't be used for the translator side of it, only for the client side. Another one for you guys. This one's called NAT64. It is 11 years old, and this one does stateful NAT64 only. So it's only the network side, the PLAT side, and 464XLAT, and it completely uses one IPv4 on its own, so it doesn't share with the Linux host. So reading the code, they have to deal with a lot of session cache because they're dealing with stateful translation. So they have all these expired sessions, etc., dealing with that. Looks like they might be able to deal with some ICMP, so here they can deal with informational. For errors, they can deal with time exceeded, but none of the other ones, which is an interesting choice, I guess. So this was probably at one time adequate, but not great. Now one quirk I'll notice that the stateful translators have to deal with, the stateless ones don't, is kernel modules don't have a ton of access to netfilter. So netfilter is the Linux packet filter, formerly called IP tables. Part of a broader system called netfilter. So in netfilter, how you deal with packets and trying to intercept like the core packet processing mechanics of Linux is not really something that a kernel module can do. So some of them get around it in different ways. This one, I believe, gets around it by creating a whole interface, so it acts as like an interface driver. You route packets to it and it routes packets back. That's how a lot of them work. But it also means it can't masquerade and share the public IPv4 address the host is using. Also in CLAT land, I have the CLAT that's used by Android, part of Android open source. And this is actually written in eBPF. So eBPF is a kind of a special thing, but it's done in eBPF, and they've done some choices that make this code very simple and very limited. So in Android, they're specifically only dealing with the CLATs. They're only ever going to be a client, never going to be a network device. They're only ever going to do one of them, and they know they always have access to a full /64 via Slack because Android doesn't support DHCPv6. So they can always generate their own IP address suffix as long as they do duplicate address discovery. And this means that they can rely on translation that's checksum neutral. So the IP checksum used by IPv4, IPv6 doesn't have a checksum, but IPv4, TCP, and UDP is really simple, and it's really easy to find a checksum collision if you have like 8 to 16 bits you can tweak to work with it. So Android has decided they're going to compute an address that's checksum neutral so that their BPF module doesn't have to do any checksum adjustments at all. And another thing Android has going for them is their Java code actually can deal with CLAT as well. So they have a more complete implementation in Java that I'm not actually sure if they still have, but for a long time they had this, and it can deal with more of the complex transfer cases. So the BPF program running in kernel only had to deal with the very simple straight-through packets. And it was only going to ever have one address to translate its own address. It was only ever going to have one prefix. It was never going to have to do checksum adjustments. It's very simple, but also very fast and efficient. And this is the code that's in millions, probably billions of Android phones around the world now. So if you're on a network with 464XLAT, which at this point is quite a lot of mobile networks, you're probably using this IPv6 to IPv4 translator. And it works well. So next up, we have Network Manager. Add CLAT support using BPF program. So this is a commit written by Mary Strodel that still has not been merged yet, but she's been working on it pretty hard, and I'm very happy to see this go. So essentially, this is going to be for Network Manager for Linux, and it will let Network Manager look for IPv4 option 108, IPv6 only preferred, look for the pref 6.4, and when all those conditions are met, enable its automatic CLAT. So this is similar to what Apple can do. On Apple, if you hook up to an IPv6 only network or an IPv4 dual stack network that has option 108, it'll automatically turn off v4 and work v6 only, which is really cool. Microsoft can do that, but only on cellular interfaces for some dumb reason. Android can do this, but again, not with DHCP-v6. And now Linux, hopefully, will be able to do this with Network Manager. So this would mean when clients connect to a network that provides NAT 6.4, they get that CLAT functionality. And again, because this is a CLAT, the function is much simpler. So Mary only has to translate between one address, her own. We know the pref 6.4 comes from the network. We're in a really limited set of conditions that mean the CLAT code is very simple compared to handling the wide variety of conditions that a network-side translator would have to deal with. But this is very functional. I'm really excited to see this go forward because this will make a really big improvement to Linux IPv6 only support, I think. Next one I got for you is Joule. You might have heard of this. This can do basically everything. So they can do NAT 6.4 stateful, they can do stateless sit. They're working on a version that can do MAP-T. That is a release candidate right now, and that's cool. And that's MAP-T on the server side too, not on the client side. So Joule is developed by NICMX. I believe that's an organization for Mexican service providers. And so this is more focused on the network side, like I want. So this can act as a full stateful NAT 6.4. We get our packets from our v6 only clients, we translate them to the v4 internet, they go on their merry way. This can also act as the client side, it can act as a data center gateway, and they're working on adding MAP-T support. So MAP-T, we've seen MAP-T client implementations already, but those essentially look just like a CLAT, pretty much. But on the network side, it's very different. So the whole point of MAP-T is that we don't have to run a stateful NAT gateway in the carrier network level, because that's a lot of state tracking for carrier-grade networks, and it's one of the reasons why they hate carrier-grade NAT. So with MAP-T, we essentially assign a range of ports to each subscriber statically. So we have to look into the layer 4 header, like TCP or UDP at the port numbers, to look up which subscriber it goes to. So we're looking deeper into the packet than just into the IP header. But we still have to maintain state. So there's RFCs to deal with this. Joule is working on implementing them. Joule is built as an out-of-tree kernel module. So it runs in Linux in the kernel. But it's not part of the Linux source tree, it's not compiled with the kernel, and that gives it some big quirks. So here's a basic picture of how NetFilter works. So when NetFilter packets come in, we have the option to look at them with XDP. If we're using XDP, we pass them on to bridging. So if you deal with anything that does layer 2, it goes to the bridge layer, or it gets kicked up to the network layer if we're doing routing. Here it can go through raw, then it can go through contract, mangle, NAT, routing, firewalling, and then the output side. So the firewall actually happens either here for input or here for forward. And the routing happens right here at this point, and contract happens way back here if we're doing NAT. So for out-of-tree kernel modules that want to implement this in Linux, they don't have access to hardly any of those things in NetFilter. So the only interfaces that Joule has in the kernel is in pre-routing and post-routing. So pre-routing happens before we've even looked at contract, and post-routing happens right before we toss the packet into the network card. So essentially, the packet comes in from the network card, we get to look at it in the NF table pre-routing rules, and right there we decide if we're going to kick it to Joule or not. And from there on, Joule has to implement everything else on their own. So we've skipped over contract, we've skipped over NAT, we've skipped over routing table, we've skipped over the firewall, and all of that has been done either by Joule or Joule doesn't do. So if you use Joule, first of all, packets have to come in from the network interface. So if you try to use the NAT 6.4 from the NAT 6.4 translator itself, it won't work, because it only translates packets that actually come in from the network. That's a really, really weird quirk. Side effect of that too is that it also can't deliver packets to the local system. It can only translate them for someone else. We can't reuse that address very well. There's a little bit of thing we can do to reuse that same IPv4 address for the host itself. It is possible. We skip over the firewall entirely. The routing table is processed in a very simplistic way because Joule has to do it on its own. It's just kind of a mess. So if you're building out an ISP level system where you're dedicating this whole box to running Joule, that's fine. You have weird configuration, but that's it. If you're doing this on your local system, any way that you use Joule, you have to use a network namespace with a virtual Ethernet bridge and things like that, because any other way, Joule is just going to leak and do its own weird things. So that basically means that Joule can't run in a container. It has to run its own network namespace, which means you can't run in any sort of isolated environment that prohibits namespaces, like a container. And you can't use it on your own unless you do this weird isolation stuff. So it's a great project, but it's very weird to run. So it'd be nice if we had something that was a bit more standard. And for that standard, we have Taiga. Simple, no fuss, NAT64 for Linux. Now, this is a bit on the old side too. So the latest version was released here at littech.org in 2011. So that puts us at 14 years old. And it works with Linux kernel 2.4 and 2.6, so you know it's modern. But it's really simple, and it's a complete implementation, and it works well. Now, I know it says it hasn't been developed since 2011. Now, the original author has not developed it since 2011. He's only posted that tarball there on his website, and that's just kind of the origination of Taiga. That said, other projects have been maintaining patches against Taiga for years. So FreeBSD maintains their own patch, because this only works with Linux 2.4 and 2.6. Debian has 10 patches they've been maintaining against this over the years that add some functionality, fix missing problems. I added a patch to add RFC, was it 8125 I think it's called, the local use well-known prefix, because it would previously drop those packets on the floor. But this is a complete implementation of all of the features of SIT, at least the first 6. It doesn't do hairpinning. But it does everything else entirely thoroughly correctly. So it's fully translating all ICMP types, as far as I can tell, all IPv6, all the weird corner cases. Taiga has figured that all out 14 years ago, and it still works. It's just not very fast. So I've chosen, as my contribution to the IPv6 world, to adopt Taiga, and I've made it its very own GitHub page. So here we go, apple.art/Taiga. Taiga NAT64 daemon. You can see I've been doing some work on it. But basically I started by taking the tarball from Nathan Luchansky and all 10 of Debian's patches and FreeBSD's patches and just overlaying them all on top of each other and committing that. So I did a release on GitHub here so you can see the source code. This is basically the current state of how things are in the major distros. So Debian has their patches. The Fedora side of the Linux system has the exact same 10 patches as Debian. I think they actually have 9 of them. They don't have my patch. But whatever. So those are all what people have actually been using with the patches that have been sent to these Linux distro projects, because the origin, littech.org, hasn't published anything in 14 years. So I'm hoping to bring this all back into one unified space instead of having every Linux distro carrying their own patches around in FreeBSD, and also start to implement RFCs which post-date 2011. So the main RFC that actually deals with translation was completely rewritten. Most of the logic is the same, but it included a whole bunch of new updates on 10 years of experience in building packet translators. None of that's in Taiga because it follows an older version. Things like that. So that's my goal. So I brought the 2 real good solutions down here for some bandwidth testing. Now we have Joule, the quirky out-of-tree kernel module that promises excellent performance if you can deal with its wild side effects, and Taiga, the user space NAT64 translator that probably will not have great performance because it runs in user space. So here's my test setup here. I have a wide variety of systems to run with. I wanted something that was very low end because all of my networking gear here is 10 gig, so I'm not running it like 100 gig. And when I'm pushing 10 gig of packets, really any of these systems should probably be able to handle at least a couple gigabits with either of these solutions. And since I didn't want to max out Joule, the more performant implementation, at 10 gig network bandwidth, I needed a system that was so poorly performed that it would be bottlenecked by both of my solutions. So I got this guy here. It's a AMD, was it 5600? It's like some really old like construction equipment CPU. I think it's got 4 cores, although you might call that like 2 cores, 4 threads because of how AMD split up stuff before. But yeah, this thing's not very good for performance. I've got an Intel X520 10 gig network card here. This is actually doing traffic in both directions, but since traffic goes in and back out, I can do 10 gig testing if it's unidirectional. And so this 10 gig connection is hooked up to my other systems. And from there, I can generate 10 gigs of traffic, send it through the NAT, receive it back on the other side, validate it. So pulling up my data now. So with Joule doing stateful NAT64, I was able to peak with full line rate MTU packet sizes at 7.44 gigabits per second. It's a 1500 byte MTU, testing single TCP stream and iPerf. So that's like an absolute best case. Taiga, meanwhile, without doing NAT, just doing the IP ICMP translation, was able to get to 0.85 gigabits per second. So that's about a 8 times improvement in Joule. And if we actually want to do address and port translation too, we have the Linux kernel do NAT44 masquerade, and that brings us down to 0.73 gigabits per second. Rather slow. So, since I'm adopting Taiga now, I guess this performance problem is my problem. I really like how easy Taiga is to use, how simple it is to set up, how wide of a configuration space it can implement, which is sort of unlike Joule. But the performance penalty is pretty killer if you're running like a whole network. If you're just doing one system as a CLAT, it's probably just fine. But when we start deploying this for NAT64 and network level implementations, running it less than gigabit's is not going to cut it. Obviously, I could move to a higher performance single core system, which this is an Intel, so it probably would clock pretty high and be fine. But even then, we want to push like hundreds of gigabits through this system and not like crap. So, my 4 ideas on how I can make Taiga better. First one, use IOU ring. Second one, use segment offloads. Third idea, use an eBPF shortcut helper. And fourth idea is use multi-threading. So with both Joule and Taiga here, I was actually bound by a single thread for this test. Part of that is because of how Joule works. Joule works in the netfilter kernel interrupt. So that happens in the processor core that processed the incoming packet. So it's essentially bound to whatever the consistent hashing of the network card does. So since all of my TCP streams had the same source, destination on all 3 layers, they all get sent to the same queue and they get processed by the same core. Running a multi-core system with Taiga should scale out much better because it will handle multiple cores, just not for a single TCP stream. Taiga, though, is purely single-threaded, so all the packets get processed entirely sequentially, which means it can never scale more than the performance of a single core. Now, Taiga uses the generic TUN-TAP adapter to send packets to and from the kernel, and at least on Linux, this can be multi-threaded. You can open more than one file descriptor on the same tunnel and have them all process packets in parallel. That's a fine thing. The only thing I would have problems there possibly is with Taiga's cache and address map. So there are a couple cases in Taiga where we access global state, one of which is the address cache. So it caches commonly or recently translated addresses and keeps track of if it's seeing flows in both directions, if it needs to fragment packets for them due to MTU reasons or things like that. So those are kept in cache, and every time we update cache, we'd have to do some synchronization, which would be not ideal. The other thing that could happen is we allocate addresses from the dynamic pool. So if we see a new IPv6 address going to an IPv4 destination, we might have to give that IPv6 source address a temporary v4 address to use for a while. And that allocation obviously would have to be synchronized. It's not that big of a challenge, but it's something to think about that Taiga was never designed to do synchronization every time it writes to global state, because it was designed to be single-threaded where that wasn't a problem. So multi-threading is on the table, but not my first choice. Next option is IOU ring. So IOU ring is a feature on Linux that allows you to create a ring buffer of commands and responses to the kernel. So this way, instead of doing the traditional system call method where we call poll and then we call read, and then we probably are going to call write again to write our new packet back in, that's 3 system calls per packet. What we could do is we could write a ring buffer and basically fill the ring buffer with a whole bunch of reads, and as they come in, the kernel will process those reads, send us the data. We can then write our writes back into the command queue and process everything without having to do a whole bunch of jumps to and from the kernel. Now, some people have seen really big improvements using IOU ring, especially in the land of SCTP. So there's a developer who I know that works on Osmocom. I'll link a video up here where he talks about IOU ring. So he was actually one of the original guys that wrote IP tables, and he moved on from that, and now he develops open source, like 3G, 4G, 5G, 2G even, software for Linux. And that relies a lot on SCTP, Stream Control Transmission Protocol. And the SCTP implementation is not fantastic in Linux. So he relies a lot on IOU ring now to really speed up his stuff that's dealing with a wide variety of packets and sockets and things like that. So that's an option too. So the next idea is segment offloading. Now, one of the big challenges with dealing with IP packets is that they're actually really small. So IP packets are only 1500 bytes by default. IPv6 guarantees they must be at least 1280 to transit the wire. We have jumbo frames, which gives us a 9000. So we're doing a decent amount of work in code for only 1500 bytes, or even less than that, of actual data. So if you're sending megabytes or gigabytes of data, you're going to handle thousands, tens of thousands, millions of packets. And that means that all the code in Taiga gets executed like 1,000,000 times per second on 1,000,000 packets, which is outrageous. So any optimization there would help. But if we could deal with this like much less, it would help a lot. So a lot of network cards, especially for TCP, can do a function called segment offloading, where if you get 10 TCP segments all in a row, you can put them all in one buffer with one header. And the network card will check that all the segments are sequential, correct, etc. And then Linux can process that as one packet that's 10 times as large. And so we can go up to the maximum MTU of 65535 or 64K bytes. Taiga doesn't support that, so every packet has to get sent to Taiga one at a time. But if we added support for the offloads, then at least for TCP, we could take care of a couple to maybe a dozen packets with one trip through the kernel and system calls and things like that. So last idea is to use eBPF to write a shortcut. So eBPF is the extended Berkeley packet filter. The original Berkeley packet filter was just a packet filter, and essentially you could use a sort of virtual machine bytecode language to write code that would run in the kernel on every packet and decide if it should be filtered or not. And this meant you had to do no round trips to user space because your code was running in the kernel. And it uses a formal verifier to run through the bytecode and make sure that it's not going to do anything dangerous, which also means that it's really hard to write because you always have to please the verifier. But if you can please the verifier, you can do relatively small amounts of packet processing in kernel on every packet without having to transition to user space at all. So I've already mentioned there's a couple different implementations of NAT6.4 in BPF. But since Taiga already is entirely compliant with full IP and ICMP, we don't actually have to translate all of that code into BPF because we still have the user space Taiga. So what we could do in this case, because Taiga already works very well, is we could have Taiga create a BPF helper on its own interface. So every packet that comes to Taiga, the BPF code could look at it and say, is this a data packet? Because data packets are way easier to translate than ICMP packets. And if it's a data packet, and maybe we already have the address in cache, we could translate that in BPF in the kernel with a small amount of code and let the user space Taiga handle all of the complex scenarios. So if we get an ICMP, ICMPs aren't that common, so we can handle all of those in user space and be just fine. If the packet has to kick back an error, we could send it up to user space and let it deal with it. If the packet goes through normally, then we could translate it in BPF and not have to do the jump into user space at all. So that would also come with segment offloading because you really can't work in eBPF without dealing with segment offloading. A lot of Linux netfilter code just assumes segment offloading works, but that comes up with that as well. So I guess with all that talk on performance improvements, I kind of skipped why I adopted Taiga in the first place. So this kind of it's come from another different things in the past. So about a year ago, I had a discussion with Nathan Luchansky, who's the original author of Taiga. I was submitting my patches to Debian at that point, and I had mentioned that Taiga is abandoned. Because at that point, I hadn't seen any talk from Nathan in like 10 years about Taiga. And he actually replied to that email thread because the Debian maintainers included him on it. It's part of what Debian's automated bug tracker does. And he said, oh no, it's not exactly abandoned, but I've been getting a lot of emails from different organizations that use Taiga asking if it is. And maybe I'll move it to GitHub someday or some of these other modern code sharing platforms like GitLab, something like that. And so I thought maybe he's going to do that, I can contribute there, and he never did. So I have now made my own Git repository for Taiga that I guess will become authoritative over time. So I hope to do like a bit of a cleanup. I've merged all the patches from Debian, I've merged the patch from FreeBSD, and I want to clean it up to a state that I feel like is good enough for a V1 release. So Taiga was always called V0.92, with then Debian's patch suffix on the end. And if I get to V1, and that's stable, reliable, with the performance it has now, I hope I can start getting it adopted into the distributions. If I can prove to them, essentially, that my code development practices are good, my testing is good, etc. So I guess that brings me on to the next step, which is testing. So Taiga never had any tests. Taiga has like 6 C files, and they're all really long with no comments. So how do we prove that Taiga works? So every time in the past that I'd made a change, and even when I submitted my patches to Debian, they didn't look for testing at all. But I basically had to construct network namespaces, try iperf, try ping, and there's only so much you can do manually to do testing. So like there's quite a lot of requirements in RFC 7915. Taiga's not even written to 7915 because it didn't exist when Taiga was written. But how do I know that it's all working correctly, that all the corner cases work? And I don't. So I decided that before I start modifying Taiga, because inevitably I will break something. If I start adding segment offloads, I will break things. That's just how development works. I need a way to prove that it's still performing correctly. And so I wrote a complete test suite for Taiga in Python. And the test suite now is about 80% finished. And so I generate some very artisanally handcrafted packets in Python. I send them to Taiga. Taiga transits them and sends them back. And I verify that all the fields in the packets are right. And if we do that several hundred times, I think the test cases now have like maybe 600 to 800 test cases. Some of them are in for loops, obviously, so there's a lot of different tweaking of bits going on. But with those test cases, we can be pretty confident that we're compliant with the RFC. That doesn't necessarily mean that everything is entirely correct, because even the RFCs could overlook things. But at least we've met all of the requirements laid out by the RFC in a wide variety of cases. So that's the test suite. Test suite tries v4 to v6 and v6 to v4 data translation, a bunch of cases that'll cause ICMP errors to be kicked back, thoroughly translating ICMP packets, which is actually a huge part of the code. Test code is all the different ICMP cases, which are so broad and complicated. Also other cases like translating all the different address modes. So Taiga is one of the only translators that supports a NAT64 prefix that's not a 96-bit prefix. So if you just take 32 bits off the end of an IPv6, which is how long an IPv4 is, get a 96-bit prefix. And literally everyone assumes you have a 96-bit prefix except Taiga. So the RFC says it could be 32, 40, 48, and there's like 6 different options, and Taiga supports all those. So that means I have to run test cases through all 6 of those, or 10 of those, or whatever, which is fine. It just takes time. And things like that. So Taiga is really full-featured, and that means there's a lot of test cases. So now that I have a test suite, I need to finish the test suite, I've also uncovered quite a few really minor bugs in Taiga. Some of them are cases where the standard was updated, so RFC 7915 is currently authoritative, but previously it was like 6145, I think. That's what Taiga was actually written to. So some things changed in the standard, and Taiga was never updated. New standards were published. RFC 7757, EAM was written. Someone actually wrote a complete patch for EAM and submitted it to Debian and Fedora, but it's not entirely complete. So like there's cases where you would have an address map that doesn't have the same suffix length. So like an IPv4, you could use like a /24, which has 256 addresses. An IPv6 that would correspond to a 120. But say, for example, you map that as a /64. Now all your addresses get shifted over. The patch doesn't handle that. We could argue if we patch should handle that. Cases where you overlap addresses. So say you have a public /24, you put the whole 24 as one map in. But then you want to override one IP, so you put another map entry in that overlaps. Now you have overlapping entries. If packets go the backwards way, which one do you use, etc. Taiga doesn't handle that correctly either, which again could be considered a bug. The RFC even says that this is probably a configuration error, but we should support it anyway. Things like that. So I've uncovered a couple bugs like that. The only real bug in packet processing was that one ICMP error had not been translated correctly, and parameter problem pointer indicates error was not translated correctly. Pointer indicates error is a really weird one to translate. I can see why he didn't write it to begin with. So in general, Taiga's proven very standards compliant, but still had a couple of bugs because obviously no one wrote test cases in 2011 and no one wrote them since then. So now look at the issues I've filed on GitHub now. I've got about 50 of them. And so like this, Taiga drops ICMP address unreachable instead of translating. That was a minor bug. Static map entries don't work until they've seen a packet 6 to 4. This was introduced by someone that did EAM patches. Taiga drops certain ICMP packets. This is, again, this has an RFC now but didn't back then. Taiga drops parameter problem packets. That's the one with pointer indicates error, previous D, etc. So anyway, after writing this test suite and reading through the authoritative RFCs, I have a much better understanding now of how much far ahead Taiga is of a lot of these competitors. So I mentioned earlier that some of these guys only did TCP and UDP, they didn't even do ICMP, and there's just so many nuances to all these different corner cases you can hit when translating v4 and v6 packets that most of these other translators just drop, and you have no idea what was wrong. They might not even send a kernel message log, they're just dropped on the floor. And so Taiga, by sending back these ICMP errors, is like doing a really good job at least following the RFCs, even if it's maybe a questionable behavior to send all these error messages back. It's what we should be doing. So what I need from you guys, I specifically have these issues that are labeled question, and that's where I essentially have a question for other people. So I got 1, 2, 3, 4, 5, 6, 7, 8 questions that I would like experts to help weigh in and answer. And so I'm going to walk through each of these guys. I'll just open a bunch of new tabs here. So here's one that I actually wrote all the code to fix. So section 4.2 RFC 4844. I wrote all the code to fix this and then decided that I didn't actually like it and I reverted it. So I want your guys' input on this specific one. Here in the RFC, it just kind of casually mentions, if we receive a packet that contains an extension, RFC 4884, then that will change the packet length and we'll have to update the extension length attribute and etc. How to deal with these RFC 484 extensions. So for those of you that have never seen it, this adds extended messages to ICMP, which seems like it'd be super useful. So anyway, these ICMP extensions, I have not found any tools that support them. Maybe some of you that work in the industry can tell me if these ICMP extensions are well used in the wild. Essentially, in theory, what can happen is if you get an ICMP error back, normally it includes the packet that caused the error, at least the beginning of the packet. And so what this does is it adds an additional header that says a bunch of optional information, including like what is the name of the interface on the router that got the error? What is the index of the interface? What is like, so it can say specific things like this packet came in at ETH0, and ETH0 is what caused the error. And this was the specific IP address of the interface, not just the router in general. And I guess that could be very useful in troubleshooting. The one other extension that's defined is the MPLS label stack. So if you do MPLS, which I don't do, and you get an error in the MPLS chain, you can translate that MPLS error into, when you kick back an ICMP error, adding the MPLS label stack. So you can debug your MPLS setup. And I guess the MPLS one is used by people that do MPLS. I don't do MPLS, so I can't say. So the code for translating this looked ugly. I was not happy with it. This RFC is very much a hack. And so if people actually use RFC 4884 extensions, I'd love to hear about it and if Taiga should support translating them or not. This one's similar. If we get an ICMP extension, should we translate the address from v4 to v6 or not? I don't know about that one either. This one is, again, extended next hop info. This is, again, an ICMP extension. So this extended next hop info, that's the extension I mentioned earlier that includes a bunch of information about the interface on the router which generated the error. And so one of these RFCs that postdates Taiga also discusses in depth what to do if we can't translate the address of an error packet. So imagine, for example, we're doing 464XLAT. So the host is sending v4, translating it to v6, sending it over v6, gets translated back to v4. Imagine a v6 router on that path generates an error message and sends it back. Now we have no way of mapping that v6 address to the v4 address space because it just doesn't fit. So what we do in this case is we use our own address because we need the error message to get back to the host so the host can deal with the error, especially for path MTU discovery. So what Taiga will do is it will use its own address as the source of this error. And there's an RFC that has a bunch of different options on how you can handle this case. And one of the things it says is we should add an extension that says the v6 address of the origin when we faked the v4 address. And we obviously don't do that because that whole discussion was newer than when Taiga was written. So if you think that would be useful, I don't know of any tools on Linux that support that extension, but if you know of some, then that'd be very helpful to me. Next, I've got two here that deal with RFC 7757. This was a support that was kind of hacked in by a contributor in 2018. And so do we deal with unequal suffix lengths, and do we deal with overlapping v6? So RFC 7757 says we could conceptually have a prefix of, say, 203.0.113.0/24 on the v4 side, and on the v6 side we could turn that into something that's not a /120, and we should translate that correctly, and Taiga doesn't. Now, I don't know who's using explicit address mapping. This would be part of SIT-DC for data centers. I don't know who's using this with offset bits. So essentially what would happen is we have an 8-bit suffix from the v4 address. If we suddenly have a 16-bit suffix length, we would shift them over by 8 bits, which seems really stupid to me. I don't know why the RFC would tell us we can do that. Taiga doesn't do it. If that'd be useful for you, then write this in the comment, otherwise I'm going to close it. And similarly, overlapping v6 directives. So I mentioned earlier how you could have like a /24 with an overlapping map directive with a /32. In that case, the v6 translations would be different. So what happens if a packet comes in destined for a v6 address that has an overlapping entry? How do we translate that? Does that break everything? Currently, Taiga will basically just throw out a bunch of these directives and tell you that your config file is invalid, you need to fix it. And that seems like a pretty reasonable choice. It'll deal with the v4 side correctly. So if you have a /24 mapping plus a /32 mapping that lands inside it, all of that is dealt with correctly. What's not dealt with is the same error on the v6 side. But in my opinion, v6 has so much address space that you shouldn't be overlapping things at all. So Taiga's behavior seems reasonable even though it's not compliant. And if you agree or you have a reason that that's a problem for you, I would like to hear about that as well. So I've also got this idea as an increasing throughput. So these are my 4 ideas I mentioned earlier: IOU ring, segment offloads, threading, and eBPF. I've actually already dabbled in several of these. I mentioned earlier the challenges of multi-threading. Multi-threading could obviously work well. It's always going to be subject to consistent hashing in Linux. Linux is never going to send us packets from the same TCP stream on the 2 threads. That's not going to happen. I've dabbled in IOU ring. Some reports of people that write VPNs, like Cloudflare, for example, has a whole great blog post on comparing some of these things in the context of writing a user space VPN, which are a lot of applications that use the same TUN-TAP adapter interface. They found that IOU ring didn't help them a lot. It's possible that's specific to VPNs and not to Taiga. I don't know. It seems like IOU ring would help a lot, but I don't know about that. Segment offloading helped Cloudflare like massively. They got like a 7x performance improvements from using segment offloads with TCP. Then again, a lot of their traffic that they handle is TCP. So if you happen to use Taiga in a more UDP environment, UDP segment offloads are much newer in Linux. A lot of network cards don't support them. So it's really going to be a TCP optimization, which still TCP is a bulk of internet traffic, at least for now. It wouldn't help with Quick or things like WebRTC, which maybe that's like what your network deals with a lot. So these are my ideas. If you have any other additional ideas you'd like to contribute, you're welcome to add them here as well. So develop a container file and container documentation. I kind of started this, but it's not thorough enough, I don't think, so I'd like some input on how you guys would use this. So, like I said, I was trying to run NAT64 on a MikroTik router. They support OCI container images if you upload them as a tar.gz. And I wrote a container file for Targa that starts an Alpine container, builds Taiga, generates a new container, copies the binaries over, etc. And that worked fine. The performance was awful, as you expect, running on like literally on a network switch. It's like a 1.4 gigahertz ARM 32-bit network switch, but it worked. So I wrote a container file for that specific use case as a NAT64 translator. Obviously, I think it'd be more useful to people as a CLAT though. So I imagine that there are some people that have IPv4 only legacy applications they're trying to run in, like, say, an IPv6 only Kubernetes cluster. And if you could load Taiga as like a sidecar pod to do v4 to v6 packet translation for you, maybe that'd be very useful. So if you are in a highly containerized environment that deals with these kinds of things, I would like your input on how to best structure this container. So for this to work, Taiga will need its own IP address, or it will have to do IPv6 masquerade, which can be done in Linux just fine. It'll create its own IPv4 address and default route. I can manage that on my own. But how would you want to configure a sidecar container? Would you want to create a container as a first-class citizen, create a v4 only Docker network or something like that? Or would you rather have a Taiga side pod that gets added to every single container to translate that one container from v4 to v6, things like that? I'm looking for input on that kind of thing. And if you have any other use cases, obviously, I could build these as separate container images like the NAT64 use case image, the sidecar use case image, so you don't have to overlay any configuration files or things like that. But if you have containerized usage input, write it here. And last one, I want to build a CI/CD pipeline. So I have the full test suite. The full test suite takes a little while to execute. So I'd like to write a simpler test suite that can run in Docker and in Podman that just tests the basics. And then we can use GitHub CI to generate the image, push it to the container registry, etc. So far, all my container development's done in Podman. So I have a container file instead of a Docker file. I use Podman build instead of Docker build, which seems to be unpopular, but I'm sticking with Podman because I hate Docker branding a container as their thing when containerization is so much more than just Docker. But anyway, I think this would be useful to a lot of people for the reasons I mentioned in the last one as well. So as for my open issues, what else do I got? So I'm going to write unit test cases. This is mostly on me. I'm concerned about the cache possibly causing memory leaks. Not that 8K entries is bad, but I mean, could cause problems. MAC4, MAC6 differing can cause cache problems. These are the kind of things I want to test in unit testing. And no, we're not going to rewrite any of this in Rust to fix memory leaks. That's not how this works. Yeah, so I've got some other options that I want to fix, and that's basically how I'm managing my GitHub right now. So that's kind of where I'm at now. Now I can handle the coding stuff on my own. I actually work professionally as a C developer, so dealing with low-level memory safety concerns is like my jam. And so is writing test cases in Python, actually. That's a big use of Python for me. But what I could really help with is people that have experience in other networking domains other than the stuff that I deal with. So if you have experience in those weird extension headers or things like that, that would be really valuable to me on the GitHub. If you're into containerization, that's again something that I don't really do, and how Taiga could help you there would be very useful input to me. Other things going on, I have a Ko-fi. I don't mention the Ko-fi that often, but it's sort of like Patreon, but it's only a one-time donation thing. I really appreciate all those guys. I have a link down below for that. I should probably add it to my GitHub. I haven't done that, but I'll probably do that eventually. If you have comments that are very related to Taiga, you can put them in the GitHub issues. Otherwise, I have a Discord server, which is a great place to message me. So link down below for that. You're welcome to chat with me there. I greatly appreciate talking to all of you guys about all the wacky things you do in networking, home lab, virtualization stuff, Proxmox, etc. And so, without further ado, I guess I'll see you guys on the next adventure.